step function. Laplace transform always involves a unit step function. And then this is just ut cosine of t. Okay, example 11.16, example 11.17. Then you're given something that looks like this. H hat of s is equal to s plus 1 over s minus 1. Okay? And then you do a partial fraction. You can do a partial fraction very easily. Partial fraction expansion. And then after that you can find your impulse response, which is the unit step function with the minus 1. And then the other one is just e to the t ut. Okay, I think most of you know how to do that, right? Partial fraction, then table lookup, partial fraction, and table lookup. Okay, very simple. So example 11.18, you are given a function that looks something like this. And then you do a partial fraction, okay, k1 over s plus 1 squared plus k2 over s plus 1. You have to add the pole of multiplicity 2 in order for this to balance out. Otherwise, the equation doesn't balance. And then you can find k1 and k2 through a very simple procedure. And then you do a table lookup on this. Okay? Do a table lookup on this. And what is the Laplace inverse transform of 1 over s squared? Does anybody remember? 1 over s is the Laplace transform of what? 1 over s, Laplace transform to what?
1.
1? Almost correct, but not quite correct. Yes?
ut.
ut, okay, unit step. Okay, 1 over s squared, Laplace inverse transform to tut. Okay, you can look that up. And you can also derive that quite easily. And then you can look up the inverse Laplace transform of these two terms and then do a shift. There's a frequency shift. Okay, frequency shift corresponds to what in the time domain? Frequency shift corresponds to a no, exponential function multiplication, a modulation by exponential function. Okay, so you will see that when you shift in frequency, you actually have the modulation with this thing. Okay, like e to the minus t ut. Okay, you see this kind of thing. Okay, and let's see, I have 10 minutes left and many examples to do. There are lots of examples in this section. Let me see how many can I do within this 10 minutes. Okay. Okay, example 11, section 11.2.3. These are quite interesting examples. H hat of s is equal to s over s plus 1. Now the numerator is not necessarily of lower order than the denominator. So we have to write this in a fashion so that the numerator is of lower order than the denominator. So we can write this as s plus 1 minus 1 over s plus 1. And then when I have s plus 1 divided by s plus 1, I have this. That's my thing. And then what thing Laplace transform to 1? What thing Laplace transform to 1? What is the inverse Laplace transform of 1? Yes, remember that?
Delta.
Delta function. So if I do h of t now, okay, that thing is just a delta function. And then the other one Laplace transform to something like this. Okay, the other one Laplace transform to something like that. But I can also do another trick. Another trick is to write this as h hat of s is equal to s of g hat of s. And if I see an s relationship, what do I know their relationship should be in the time domain? Okay, say ht must be equal to gt. What do I have to put over here?
Derivative.
Derivative, very good. Okay, derivative. So I can find the Laplace inverse transform of this and plug it in here and do a derivative, and I should get the same answer. And that gs, you can say that g hat s is just equal to 1 over s plus 1, right? G hat s is equal to that, and then this inverse Laplace transform to something like e to the minus t ut. Okay, and if you differentiate this one, you get this one. Okay, that's a second way of doing that problem. And then I do example 11.20. And in this example, I'm given something that looks something like this. If hat of s is equal to s squared plus 1 over s squared plus 3s plus 2. Okay, so what I need to do then is to write this as equal to, I do a division because the numerator is of the same order as the denominator. I do a polynomial division and obtain something like this. Okay, I can also factorize the denominator so that it looks something like that. Okay, next thing I need to do is to do a partial fraction. So I get 1 plus 2 over s plus 1 minus 5 over s plus 2. I get 5. I'm not sure if I get it correct. Okay. Yeah, it seems that it's 5, okay? It's 5. And then I can do the inverse Laplace transform now. This one Laplace transform to a delta function. The other one just Laplace transform to exponential functions. Okay? Exponential functions. Maybe 2 ut e to the minus t, and then it's 5 ut e to the minus 2t. Something like this. Okay? Is this clear or not clear? And then I have example 11.21 where g hat of s is equal to s cubed over s squared plus 1. Again, I can do this using two tricks. I can take the s outside and have s squared over s squared plus 1. And then I try to find the Laplace inverse transform of this. And that one is equal to 1, okay, minus 1 over s squared plus 1. And then you can factorize this. You can factorize the denominator. And then s, 1 minus s plus j, s minus j. And then you can partial fraction that one. Okay, you can partial fraction that one. And it partial fraction to something that looks like a cosine when you Fourier inverse transform it. Okay? But so you can write this thing as a time derivative in the time domain, find the Laplace inverse transform of that part and then differentiate it with respect to time. Okay? And that is one way you can do that. Okay? And then let me see, I have done 11.20, 11.21, 11. 19. Yeah, I think the rest are very simple. You can do them yourself. Okay, I think I only have 1 minute left. And you can ask any questions within this 1 minute. So you know how to do Laplace inverse transform now. Laplace inverse transform is just Fourier inverse transform in disguise. The easiest way to do that is just table lookup. You cast your function into a form that you can find in the table.